Hello everyone and welcome back to the channel. Now before I begin today, I want you to do one thing. Just pause for a second and think, what happens to a pendulum when its length is slowly decreased while it is still swinging? Does it swing wilder? Does it calm down? Or does it stay the same? And here we are going to not just answer this, we are going to derive it step by step with complete mathematical rigor. So this is the problem in front of us. A pendulum bob of mass m is attached to a light inextensible string. This string passes through a small hole in a horizontal board. The bob hangs below the board and swings freely. Now a person standing above the board slowly pulls the free end of the string upward. As a result, the effective length of the pendulum gradually becomes shorter and shorter while the pendulum keeps oscillating throughout. Two very important conditions are given. Number one, the accelerations are small, and number two is the pulling is slow enough that the motion always remains smooth. The second condition is what physicists calls a quasi-static process, and it is absolutely central to this entire problem. Now, three questions are being asked. Question A. Does the angular amplitude, that is the maximum angle the pendulum makes with the vertical, increase, decrease, or stay the same? Question B. Does the linear amplitude, that is the maximum horizontal displacement of the bob, increase, decrease, or stay the same? And C. Derive the exact mathematical relationship between the linear amplitude and the instantaneous length of the pendulum. Now, what we are about to discover is not just an answer, it is a window into one of the most profound ideas in all of physics, something that connects classical mechanics to quantum mechanics. Now, let's begin. Now, before tackling this problem, just think about it. The length is changing continuously, the amplitude is changing, the energy is changing, everything is in flux. So where do we even start? This is where we have to draw a clear strategy to solve the problem. And here is the key insight. When the person pulls the string upward by a small amount, let's call that delta L, he is doing work on the pendulum system. And by the work energy theorem, that work must equal the change in total mechanical energy of the pendulum. So we can write this as F average into magnitude of delta L is equal to delta E. The left side has the average tension F in the string, the force doing the work. The right side has delta E, the change in the pendulum's mechanical energy. And one critical thing to note right now, since the length is decreasing, delta L is negative. So when we write magnitude of delta L, that is equals minus delta L. So our roadmap for this entire solution is step 1, calculate delta E, the change in mechanical energy. Step 2, calculate F, the average tension in the string. And step 3, equate both sides and extract our answers. So, are you ready? Let's execute it. Now, as for step 1, let us calculate the change in mechanical energy delta E. To do that, we first need to establish what the energy of this pendulum actually looks like at any given moment. Let's say the instantaneous length of the pendulum is L and the angular amplitude, the maximum angle, is theta. And here we take the ceiling, that is the board itself, as our zero potential energy reference. This simplifies the energy expression considerably. Now the pendulum undergoes the simple harmonic motion, so the angular displacement at any instant is theta t is equal to theta into sine omega t. The arc length, that is st, from the equilibrium position is L into theta into sine omega t, and after differentiating it we get the instantaneous velocity, that is Vt. This is equal to theta into L into omega into cos omega t. From this we get the maximum value of the instantaneous velocity, that is equal to theta into L into omega, as the maximum value of cos omega t is equal to 1. This is our equation 1. Now the total mechanical energy at the mean position, where the kinetic energy is maximum and the bob is at depth L below the board, is E1 is equal to minus mgl plus half into m into square of V maximum. And after putting the value of V maximum from equation 1, we get E1 is equal to minus mgl plus half into m into theta square into L square into omega square. Here omega is the angular frequency and its value is root over z by L. And after putting the value of omega in this equation, we get E1 is equal to minus mgl plus half into m into theta square into L square into g by L. And after solving it, we get E1 is equal to mgl into minus 1 plus theta square by 2. This is our equation 2. Now, after one complete oscillation, when the length has changed by delta L and the angular amplitude changes by delta theta, then the new energy would be E2, and this is equal to mg into 1 plus delta L into minus 1 plus delta theta to the whole square upon 2. And after expanding it, we get E2 is equal to mg into L plus delta L into minus 1 plus theta square plus 2 into delta theta plus delta theta square upon 2. Since delta theta is small, we can ignore delta theta square, and we get E2 is equal to mg into L plus delta L into minus 1 plus theta square upon 2 plus theta into delta theta. And after expanding further, we get E2 is equal to mg into minus L minus delta L plus L into theta square upon 2 plus delta L into theta square upon 2 plus L into delta theta plus delta L into delta theta. And after ignoring the doubly small terms, that is delta L into delta theta is equal to 0, and we get the value of the E2, and this is equal to mg into minus L minus delta L plus L into theta square upon 2 plus delta L into theta square upon 2 plus L into delta theta. This is our equation 3. Now we get the change in energy, that is delta E, and this is equal to E2 minus E1. And after putting the value of E2 and E1 in this equation, we get the final value of the change in energy, that is delta E, and this is equal to mg into delta L into minus 1 plus theta square upon 2 plus mg into L into theta plus delta theta. And this is our equation 4. Now pause here for a moment. Equation 4 has two parts. The first part, that is mg delta L into minus 1 plus theta square upon 2. involves the change in length delta L, and the second part, that is mg into L into theta into delta theta, and this involves the change in angular amplitude delta theta. Right now, both delta L and delta theta are unknown. We have one equation with two unknowns. So we need a second independent relationship, and that is exactly what step 2 gives us through the average tension. And this is the beauty of the strategy we set up earlier. Each step connects to the next. Now here is our step 2, and let's find the tension in the string. The bob is moving along a circular arc at every instant. So the tension in the string must simultaneously do two things. The first one is provide the centripetal force needed for circular motion, and the second is to balance the component of gravity along the string direction. So at any instant, the tension is, that is Ft is equal to mv square by L plus mg cos theta. Now let's substitute Vt is equal to theta into L into omega into cos omega t, and we get Ft is equal to m into theta square into L square into omega square into cos square omega t upon L plus mg cos theta. And after putting the value of omega from the relation, that is omega square is equal to g by L, we get Ft is equal to m theta square into g into cos square omega t plus mg cos theta. Now, for small angles, we know that the value of cos theta is equal to 1 minus theta square by 2, and also at any instant theta t is equal to theta into sine omega t. So we get the value of cos theta, this is equal to 1 minus theta square sine square omega t upon 2, and after putting the value of cos theta in the equation of Ft, we get Ft is equal to m into theta square into g into cos square omega t plus mg into 1 minus theta square sine square omega t upon 2, and after solving it we get Ft is equal to mg into 1 plus theta square cos square omega t minus theta square into sine square omega t upon 2. Now we cannot directly use this instantaneous tension in our work energy equation, and the reason for that brings us to one of the most important conceptual points of this entire problem. Let's go to the next slide. Now here is the conceptual heart of this problem. The tension Ft that we just derived, it oscillates rapidly with every single swing of the pendulum, but the length of the string, it changes extremely slowly, almost negligibly during one complete swing. So think about it this way. During one complete oscillation, the length barely changes, but the tension has already gone through a full cycle of variation. This means the work done over one complete swing is not Ft times delta L at some particular instant. Rather, it is the time average tension F bar multiplied by the total change in length delta L over that swing. This is why we replace Ft with its time average F bar. Now, taking the time average, we use the standard results, that is average of cos square omega t over one cycle, and this is equal to 1 by 2, and also average of sine square omega t over one cycle, and this is also equal to 1 by 2. So we get F bar is equal to mg plus m into theta square into g into half minus m into g into theta square into half upon 2. that is f bar is equal to mg plus mg theta square upon 4, and we get the final value of f bar, and this is equal to mg into 1 plus theta square upon 4, and this is our equation 5. Now we have everything we need. So applying the work energy theorem, we get f bar into magnitude of delta L, and this is equal to delta E. Since delta L is less than 0, it means the magnitude is equal to minus delta L. So we get f bar into minus delta L is equal to delta E. Now substituting equation 5 on the left and equation 4 on the right, we get minus mg into 1 plus theta square upon 4 into delta L is equal to mg into delta L into minus 1 plus theta square upon 2 plus mg into L into theta into delta theta, that is minus 1 plus theta square upon 4 into delta L is equal to delta L into minus 1 plus theta square upon 2 plus L into theta into delta theta. Dividing both sides by mg, we get minus delta L minus theta square upon 4 into delta L is equal to minus delta L plus theta square upon 2 into delta L plus L into delta theta. And after manipulating it, we get minus 3 into theta square upon 4 into delta L is equal to L into delta theta. And in this way, finally we get delta theta upon theta is equal to minus 3 upon 4 into delta L by L, and this is our equation 6. Now read this equation carefully. Delta theta by theta is the fractional change in angular amplitude, and delta L by L is the fractional change in length. The negative sign tells us the change in opposite directions. When the length decreases, delta L is negative, so delta theta upon theta is positive, meaning the angular amplitude increases. So the answer of question 1 is the angular amplitude increases, and this makes physical sense. The person is doing work on the system, energy is being added, and that extra energy manifests as a larger angular swing. Now let's tackle part B, the linear amplitude, and the linear amplitude is simply S is equal to L into theta. Now taking the small change, that is delta S is equal to L into delta theta plus theta into delta L. Dividing it by S is equal to L theta, then we get delta S by S is equal to delta theta by theta plus delta L upon L. After putting the value of delta theta upon theta, we get delta S by S is equal to minus 3 by 4 into delta L upon L plus delta L upon L. That is, delta S by S is equal to 1 by 4 into delta L upon L. Since delta L is less than 0, that is, delta S upon S is also less than 0. It means the linear amplitude decreases. This is our answer, part B of the problem. Now, this is a beautiful result. The angular amplitude increases, but the linear amplitude decreases. These two seems contradictory at first, but they are perfectly consistent. The string gets so short that even though the angle is larger, the actual horizontal displacement is smaller. Now this is our step 3. From equation 6, we get delta theta upon theta is equal to minus 3 upon 4 into delta L by L. By multiplying both side LQ into theta to the power 4, we get LQ into theta to the power 4 into delta theta upon theta is equal to minus 3 upon 4 into delta L upon L into LQ into theta to the power 4. And after manipulating it, we get 4 into LQ into theta Q into delta theta plus 3 into L square into theta to the power 4 into delta L is equal to 0. Now look at this expression very carefully. Cannot we see that if we differentiate the quantity LQ into theta to the power 4 with respect to both variables, we get delta LQ into theta to the power 4 is equal to 4 into LQ into theta Q into delta theta plus 3 into L square into theta to the power 4 into delta L. And from this relation, this can be written as delta LQ into theta to the power 4 is equal to 0. And this is derived in note B. So it means LQ into theta to the power 4 is equal to constant. And this is the adiabatic invariant of this pendulum system. Now, no matter how much we shorten the string, as long as we do it slowly and smoothly, the quantity LQ into theta to the power 4 never changes. It is perfectly conserved. In slowly varying systems called adiabatic processes, certain special quantities called adiabatic invariants are always conserved. And this idea appears in thermodynamics, in classical mechanics, and most remarkably in quantum mechanics, where it forms the foundation of the quantum adiabatic theorem. So this one pendulum problem is actually touching the deepest ideas in all of physics. Now let's use this invariant to find the exact answer to part C. From LQ into theta to the power 4 is equal to constant, we get L1Q into theta 1 to the power 4 is equal to L2Q into theta 2 to the power 4, and from it we get theta 2 to the power 4 upon theta 1 to the power 4 is equal to L1Q upon L2Q, and after taking fourth root we get theta 2 upon theta 1 is equal to L1 upon L2 whole to the power 3 upon 4, and this is our equation 7. Since we know that S is equal to L into theta, that is S2 by S1 is equal to L2 into theta 2 upon L1 into theta 1. It means S2 by S1 is equal to L2 upon L1 times theta 2 upon theta 1. And after putting the value of theta 2 upon theta 1 from equation 7, we get S2 by S1 is equal to L2 upon L1 times L1 upon L2 whole to the power 3 upon 4. And in this way we get S2 upon S1 is equal to L2 upon L1 whole to the power 1 by 4. Therefore, S is proportional to L to the power 1 by 4. It means the linear amplitude of the pendulum is proportional to the fourth root of its instantaneous length. And this is the answer of the part C of this question. Thank you.